Good morning and welcome you to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 2, which is DER Integrated Distribution Network Modeling. We have seen the modeling of few DERs, PV panels, wind and storage, battery storage. Today we will see the load DER, that is the electric vehicle. So, electric vehicle is now we are integrating aggressively in the power networks because we want to reduce the global warming and the air pollution. So, the electrifying the road transport is now becoming very popular, and that is how electric vehicles are keeps on adding electric vehicles in our system, which is actually an extra load we are adding with our energy circuit. So, it has mostly batteries, electric motors, your energy storage devices and an IC engine and a combination of that to prepare electric vehicle. So, the key components are first and major component, that is a battery pack which will store electrical energy, mostly it is a lithium ion based technology. Then you have electrical motors that will convert your electrical energy to the mechanical energy and drive the wheels. Then you have power electronic converters for DC AC and DC AC conversion, because we are doing charging and then you have multiple loads also connected like lights, ACs you have in your car. So, multiple time conversion you have to also do. Then you have charging port to charge the battery from external electric power supply, and you have controller to control all the operation of this battery, that is actually battery management system. The charging discharging operation you have to control from the battery, otherwise you will lose your energy and your car will shut down in the midway. So, these are the type of electric vehicles. Mostly three types of electric vehicles are seen. One is purely electric, that is the battery electric vehicle or BEV, which use 100% electricity from grid, full electric car. Second is the plug-in hybrid electric vehicle, which uses IC engine, gasoline and as well as battery and the battery pack to drive the motor or to drive the car. So, normally what it does, it takes the energy or power to the battery and store it, and also you have a gas facility or a IC engine facility. So, if your battery discharges in the midway, always you have the provision to turn on your IC engine and drive your car. So, this is the plug-in, that is called plug-in hybrid electric vehicle. Then you have a hybrid electric vehicle where you do not have the plug-in facility, you have only the gas and the IC engine and the battery is charged from this IC engine. That means that power you are getting, that you convert and you stored in the battery, or otherwise you can store also from using the regenerative braking. That means you are braking, so you are opposing the power, oppositing the power output, that means now it will flow in the opposite direction. So, that power you can store in your battery and further you can use at later time. So, this is a typical MATLAB model of a purely battery electric vehicle, where you have drivers over here, then you have this converter, power electronics converter, as I mentioned, that will convert your DC or AC power supply. Then you have battery, major component of the electric vehicle, you have motor connected with the gearbox and then you have the wheels. So, you drive your car with the help of this vehicle body and the wheels, that will be run with this DC motor, and that DC motor is scattered from this battery supply. Okay. Then you have few dump load just to represent your AC and lights in the car. So, if you simulate this battery model in MATLAB with the help of this BMW i3 model specifications, which is listed here, and this UDDS driving cycle, which is normally looks like this, and if you run this model, then you can see mostly this model follows the driving cycle, and depending upon that SOC level keeps on changing if you give the provision for regenerative braking. This output is with the regenerative braking purposes, that whenever you will drive, its energy level is going down, whenever it is braking, so at that time that braking energy is again storing back to the battery and it is enhancing or increasing the SOC level of the battery pack. So, the charging mechanism, depending upon that, whenever you will go to charge your battery, the EV chargers can be of two types. One is onboard charger and the second is the off-board charger. We will see one by one what is that onboard charger and what is that off-board charger. Onboard charger says that is mostly done by directly from the AC electrical supply. And the power conversion methodology, that means your AC to DC conversion and then again from DC to DC conversion we do inside the battery. That means your power electronics converters are placed inside the battery and you take your 230 volt or 120 volt supply, directly connect to the charging port and your battery will be charged. So, mostly level 1 and level 2 charging technologies are used for onboard charging. What is level 1? Where we use 120 volt to 230 volt AC supply, that is our home electric supply, but the charging time is very slow. That means you may need 4 to 5 hours or 6 hours time to charge the electric vehicle. The level 2 charging, that is use 240 volt to 415 volt of AC outlet, but it is little bit of faster compared to your level 1 charging. Normally it is placed at public stations or few homes also now equipped with level 2 charging facilities. So, generally on board charging facility is present at the lower voltage level or at the home level. Second comes your off board charging, that is mostly popular and which is installed at the charging stations, where other than the power conversion mechanism which is present like AC to DC and DC to DC conversion, other than having it inside the car, you put it at the charger, that is outside your car. So, you take the AC supply to the charger, convert it from AC to DC and then you do a DC DC buck converter or boost converter depending upon your voltage level of the electric vehicle battery and then give the supply to the battery, directly to the battery. You do not need any power conversion inside the battery level. So, that is going that unlike AC charging, DC charging bypasses the vehicle's onboard charger. Generally vehicles are equipped with both kind of charging facilities, that you can give direct DC or you can give AC and then convert it to the AC to DC. But if you give off-board charging, then obviously it will bypass that on-board charging facility and deliver direct DC power supply to the battery. So, that is called a level 3 and it is a very fast charging mechanism compared to your on-board power charging, and that is typically found in the charging station and highways, where you need your car to be charged within 15 minutes or 30 minutes time. You cannot spare 5 minutes time standing in the highway, right. So, this kind of off-board chargers are present in charging stations. So, now how you can connect whenever your EV is charging from the grid, how you can connect that EV chargers or EVs with your existing AC grid facility. Generally if you see electric vehicle is a battery, right. So, it is none other than a battery. So, it is a similar arrangements kind of what we have studied, how we can connect a battery with the electric AC grid. So, if you see first one is that DC link you can obviously connect, you have a bidirectional DC DC if you have an on off board charging. So, you need not an AC DC conversion, you just connect it with the DC DC conversion and you can take the power or supply to the power. Now, I told take or supply. So, depending upon that, operation of the electric vehicle can be of two types. First one is the grid to vehicle operation, that is mostly the charging operation. You are taking power from the grid to charge your battery. So, at that time your electric vehicle is acting actually as an electrical load. Now, whenever let us say it is a battery. So, simply how we used our previous storage technology, battery technologies, you can take power out of it as well, right, whenever you need. If you need more power, That means if your load is very high and your energy price is also very high, but your car is standing or parked in your garage. So, at that time you can take few amount or little bit amount of power from that electric vehicle battery, that at least that much of electricity bill you can compensate out, or you can reduce your electricity bill. So, that is called a vehicle to grid operation. So, this is the reason that we called electric vehicle also as a DER. That means you are getting also a supply, or it can act as a source at the customer end. So, that at that time if you do with the vehicle to grid operation, at that time it act as a source. So, again you have a AC coupled charging facility as well, where you will have an onboard charger or offboard charger you can connect with the AC supply. Remember, this onboard charging you cannot connect with the DC link, mostly the offboard charging is connected. So, this is the mathematical model of a grid connected EV system. When the EV is at the microgrid or at the home level, it acts same as your battery station or battery module, just the extra thing adding that you have an arrival and a departure time. That means electric vehicles, whenever it is coming at your home at a time interval, and when it is leaving your home, when it is going your home occupants or you are going for work. So, within that time limit it has to be fully charged. So, it is returning with an initial value of energy level, then its energy level will updated. That means if it is charging, then the energy level will become higher. If it is discharging, then energy level will become lower because of this vehicle to grid support. But at the time of departure it has to be at its maximum capacity. That is the primary purpose of a car. You need your car to be fully charged. So, whenever you go to work and come back, you are not go out of your fuel, that means out of your energy. Obviously, the electric vehicle charging operation will be within the limit of its energy, and similarly your charging discharging will be also a maximum power limit, and you cannot afford simultaneous charging discharging, same like your battery pack. So, it is mostly like an battery, but a movable battery. Previously we have seen that is stationary battery, now it is a movable battery. Similar, if you connect it to the charging station, the reactive power support you can take only when the electric vehicle is connected to the charging station, because you have to have an off-board charger. You have an off-board charger, then you have an AC to DC bidirectional converter at your charging station. Normally, the car AC DC converter is not a bidirectional converter, it is an unidirectional converter. So, if you have a bidirectional converter placed at your charging station with that off-board charger, you can take out reactive power support also from your electric vehicle. So, other than having vehicle to grid support, only in the reactive active power you can also get the reactive power, same as your storage. So, the total power needed for at the charging station is the summation of the how much electric vehicles are parked or present in the charging station, then how much reactive power you can take from each and individual. The total energy level of the charging station is the summation of the energy level of each and every car, and similarly with the 4 quadrant operation of your overall charging station economy, because charging station obviously it can take power, it can give power, then similarly it can reactive power also it can give and take. So, it operates as a 4 quadrant operation and it follows this architecture. So, this is actually a circle, this equation looks like a circle equation. So, that is how this reactive and reactive power operation is managed. So, how much electric vehicle penetration we have in our country? That is mostly in our country is 30% of the private cars, 70% of the commercial cars, vehicles, 40% of the buses, and 80% of the two wheelers and three wheelers we are aiming to be converted to an electric vehicle by 2030. That is our goal in India. And in the last 5 years we have registered almost 36.39 lakhs of EVs out of 10.75 crores of vehicles registered in our country. So, you can see how much huge amount of vehicles we are registering each and every year. So, at least we are increasing with the share of the electric vehicles. And also Government of India, they are more focused on investing money or giving subsidy to build electric vehicle public charging stations of worth of and rupees of 800 crores to set up almost 7,432 charging stations. So, this is the typical bar graph you can see, which represents that how much EV penetration we have in the name of electrical two-wheelers, three-wheelers, cargo, then car and bus. So, we can see each and every year 2023 to 2024 almost we have good amount of electric vehicle penetration in our system, and we are keep on increasing it. So, with this we completed our DER part, and now we will go to the modeling of the load and the Volt-VAR controlling devices. So, first start with the load. So, the load, which is us actually the consumers, either we can specify it as an apparent power with a power factor, or active power with a power factor, or separately active and reactive power. That means, your load can be active power load or reactive power load, that we have to know. As we know from the load flow solution, you have seen that each and every bus at the PQ bus we say that how much load we want. So, other than specifying these two separately, that is obviously we can do, either you can say how much apparent power your consumer is taking with a power factor value, active power it is taking with a power factor value. So, depending upon the operation of the load, either your load can be a constant load or a voltage dependent load, and that constant can be also a constant power load, constant current load, constant impedance load, and voltage dependent loads can be modeled as an exponential load or a ZIP load. Now, we will see one by one. So, this is actually the load model, where you have a 3-phase star connected load, which is represented by P plus JQ for 3 different phases, and the voltages are also 120° apart if it is a balanced condition, and if it is unbalanced, then your angle is different, voltage and angle is different from each other. So, for a constant power loads, we consider this P plus JQ S equals to this value is constant, which is you can say major share of the total power demand, because our motor loads are mostly constant power loads. So, here with the changing voltage, to keep the power constant, your current will change, because S equals to V into I. So, if your V drops, then your I has to be increased to keep the S constant. So, that is why normally we keep this voltage level as flat as possible to reduce this current. Okay. So, this is called the constant power load. For the constant current load, we calculate the current for a rated value of the power, and we keep that magnitude of that current constant. And depending upon the voltage and the voltage angle and the magnitude, the current angle may change, and to keep the power factor constant for a constant current load. For constant impedance load, same as like constant current, we calculate the impedance for a rated amount of power, and we keep that impedance constant, and the amount of current how much it takes depends upon what is the value of voltage at the load end. If your voltage is reducing, so depending upon your this, as this is your constant, so your I will reduce. Okay. So, the example of constant current load is very rare, but generally where we want a constant illuminance level of a light or any constant output from a load or constant performance from a load, at that time we use a constant current load. Constant impedance load is mostly the resistive loads like our heaters, where the amount of resistance is constant, and depending upon your voltage level you will get the current and you will get the heating effect. Then the voltage dependent load models, generally two different kinds of load models are very popular. One is the exponential load model and the second is the ZIP load model. In the exponential load model, you can see the power active and reactive power demand for both the sides, you can see they are depending upon the magnitude of the voltage. So, if you reduce the magnitude of the voltage, your active and reactive power consumption will reduce, okay, by a certain amount. This Kp and Kq, your Zps, Ip, Pp, these are all your parameters, controlling parameters for this load model. And that depends upon your what type of customer it is. For residential customer, this constant value is different. For industrial customer, this constant value is different. For commercial customer, this constant value is different. So, depending upon that, you can see for this load category, few portion of this load is impedance load, constant impedance, few portion of this load is constant current, and few portion of this load is constant power. So, actually in our real life, these loads are mix of constant impedance, constant current and constant power. So, this ZIP model and the exponential model, preferably the ZIP model, is the most promising mathematical model to represent the real value or real life representation of your loads. Then we will move to the voltage control in the feeder. So, we have seen the generation, we have seen the loads. Now, for each and every increasing load or the variability of the load will change the voltage level, but we, as I mentioned before as well, that you want a constant voltage profile to reduce the amount of current we are absorbing. So, how we can maintain that constant voltage profile? The regulation of voltage is important for distribution feeder. First thing is that you have a radial structure mostly for the distribution network. So, if you keeps on going from your substation, your voltage will keep on reducing. So, at the furthest end the customer who is there, he will experience a very low voltage. So, that you cannot afford, right. So, some arrangements you have to be there in between your feeder arrangement, that the voltage level will be boosted to keep the furthest end voltage also constant or to a certain limit. So, what is that limit? That is standardized by ANSI and IEEE. So, ANSI C84.1 standard, which is normally follows in US or North American countries, which says that your feeder voltage has to be maintained within 0.95 per unit to 1.05 per unit. For short term operation, for very short term interval, this range can go from 0.91 per unit to 1.06 per unit. Now, IEEE standard says whenever you integrate a distributed energy resources to a feeder, then you have a variation of voltage limit. For normal or long duration operation, same as ANSI, the per unit voltage is same 0.95 to 1.05. For right through operation, for little bit of temporary voltage variation, it can go from 0.88 per unit to 1.1 per unit. For right through operation for 0.16 seconds, it can go from 1 for over voltage condition, it can operate from 1.1 per unit to 1.2. For under voltage condition, it can run for 20 seconds when your voltage is from 0.88 to 0.5. Below 0.5, you can operate only from 0.16 second to 1 second, not more than that. If you run more than that, then your system will collapse. And if your voltage level goes down from the 0.3 per unit, then it will sense as a fault, because fault means it is the voltage value is close to 0. So, if that happens, then your relays and everything has to operate, your trip circuit has to operate within 0.16 second time interval. So, majorly two devices are used to keep the voltage level constant in your circuit. First one is the voltage regulator, which is actually an auto transformer with a tap changing mechanism. Normally 32 taps are there, 16 taps for rising the voltage, 16 taps for lowering the voltage from the nominal value. So, if you can see, there are two ports, one is R and L. If it is connected with the R, that means with this 16 ports you can increase the voltage by certain amount. with, if it is connected with the L, then you can reduce the voltage by certain amount. Then how much? Generally, the step voltage regulators are used to modulate your voltage level to plus minus 10%, that means 0.1 per unit. That means you can vary your voltage level from 0.9 per unit to 1.1 per unit, having 32 steps. Within that, 16 steps are used for lowering and 16 steps for rising. So, if you see that you can do 0.1 per unit operation with the 16 steps, then each step can change the voltage level of 0.00625 per unit or 5 to 8%, 5 by 8%. So, if you have a voltage regulator connected at the bus N and you want the voltage at bus M, voltage magnitude only. So, the voltage magnitude at bus M is related with the voltage magnitude of bus N by this equation. It is V n plus 0.00625 into the tap position at which tap you are keeping it, then multiplied with the nominal voltage, and your tap position can be from minus 16 to the plus 16. Minus means lower, plus means rise. But you see, this is a mechanical tap changer, right? Means actually these taps are moving, even the switch is also moving. So, if it is a mechanical device, you cannot afford to operate it multiple times in a day. That means, let us say if you take 15 hours or let us say 30 time interval, that means total 48 half time interval you have in your day, let us say. So, that means your voltage and that your load is varying at every 48 half hour. So, that means you have to change also your voltage regulator taps 48 times. So, that means one mechanical device is experiencing an wear and tear 48 times in a day. That is, if you take half hour, if you reduce it to the 15, then it will enhance. If you reduce it to 5, 1 minute, if you reduce your time interval gap, then you have to afford more and more tap changing operation with your mechanical device, and that is not acceptable. So, we keep this safety concern or lifespan increasing constraint whenever we model a voltage regulator, and that says for the overall time interval, total number of tap changing operation must be lesser than a safety value. With this, the next voltage boosting material or the equipment is your capacitor bank. As I have mentioned that shunt capacitor banks are commonly used to help the voltage regulation by providing reactive power support. Whenever you have a experience of voltage dip, you supply Q, reactive power, and that will enhance your power factor. If your power factor is enhanced, that means your voltage profile will go up. So, you can connect your capacitor bank either as a delta connection or as a star connection depending upon which circuit you are operating. It is generally favored to connect your capacitor bank as a delta. Why? Because for delta your phase voltage is equals to your line voltage. That means, with the same voltage level, if you connect the capacitor bank in delta, then your QC will be more compared to your star connected capacitor bank. And depending upon that, if you need a single phase or two phase connection, you just take one phase out from the delta or star, then you will have a two phase or single phase connection. This is the model, mathematical model. Generally, capacitor banks are switched in or switched out depending upon the requirement of the circuit. If your circuit requires reactive power support, then you just switch it on and you will immediately get your Q. When you do not need it, switch it off and then your reactive power supply will become 0 from the capacitor bank. So, actually if you model the mathematically your capacitor bank operation, you have to have a binary variable that will represent as a 0 or 1. If switch, and that will define or that will denote the switching instant or switching status of your capacitor bank. If your switching instant is 0, that means your support from the reactive capacitor bank, reactive power support is 0. If it is 1, then you will get total amount of reactive power support from your capacitor bank. Similarly, again like our voltage regulator, this switch is a mechanical device. So, you cannot afford to multiple times switching it on and switching it out because of this wear and tear, then it will reduce the life expectancy of that switch. So, similar to the voltage regulator, you have a in capacitor bank as well, you have a switching constraint that for the total number of time interval, the total number of switching operations done must be lesser than a specified maximum limit. Okay. So, that is how the voltage controlling devices most present in a distribution system, mostly the voltage regulator and the capacitor banks, are modeled mathematically, and their operations depending upon how their operations is done. Okay. So, with that I will end today's lecture and we will continue with the modeling part in the next lecture with the distribution network model. Thank you.